Hello everyone. Welcome back to Python Challenge for All. Okay, so what is today's topic? Today's topic is about perfect numbers. Do you know what perfect numbers are? Okay, let me tell you the definition. Perfect number is a number which equals the sum of its proper divisors. Do you know what proper divisors mean? Proper divisor is divisors excluding itself. Okay, so for example, 6 is perfect because you know the six the divisors of 6 are 1, 2, 3, and 6, right? So exclude 6 and add 1 plus 2 plus 3, and this equals to 6. So this means 6 is perfect. So shall we start to find the list of prime numbers? Okay? Actually, this is a very tough question. So let's start to program to do the brute force search, exhaustive search of all prime numbers, starting from, say, 1 or 6. Okay, so first we need to define a helper function, divs function, which um, returns the list of divisors for its numbers. We tried this before, right? Do you remember that? Let's try that. So, new topic, perfect numbers. Okay. So, let's define a function, divs. The parameter is n, argument is n, and which returns the list of divisors. So the long version is like this. So initial list is empty, and for any number in starting from 1 to say n plus 1, if n percentage I equals 0, this means that n is divisible by I. And then L append I. And this will return a list of factors, right? So let's check that. Print divs, say 6. Okay, let's run it. That divs, okay. I forgot to return L here. Okay, I need to return L here, of course. So it returns 1, 2, 3, 6. If you give 24, it will give 1, 2, 3, 4, 6, 8, 12, and 24. Seems right. But this is too long. So actually we know how to do it in a very short way in one line, like using list comprehension. I for I, we'll just copy it from here. I for I in range, and if this is 0, 0, take it as a list. So we can delete all this, and this will give the same function. 1, 2, 3, 4, 6, right? If you give, say, 30, it will give 1, 2, 3, 5, 6, 10, 15, 30. I for I in range 1 to n plus 1. If n percentage I equals 0, that will be a list of divisors. Okay, so for example, so the check to see if any n is a perfect number equals perfect number or not is equivalent to sum of all divs n equals 2 times n, because the last number will be the n. Okay, so let's check that. For example, if we m in, let's use k, in range, say 100, let's print prime numbers. Let's see, let's check all the numbers up to 100, 100, starting from 1. Okay, let's check that if sum of divs k equals 2 times k, okay, print k. How about this? Let's check that, if this works fine. Oh, object is not iterable. Oh, this is not good. So this should be this one, okay? And there's, yeah, this should be correct. So only two numbers, 2 and 28. We know what 28 is like. So 28 case, yes, it's like this. So 1 plus 2 plus 4 plus 7 plus 14 equals 28. Or 1 through 28, sum of all these lists equals to 2 times 28. So it's perfect number. Good. So this works. Okay. So scan integers up to 1000 to find perfect numbers. Let's do this. Instead of 1000, 100, we can write 1001. We can run this to find that there are only 3 perfect numbers up to 1000, in the range up to 100. How about it takes to search up to 20,000? Okay, let's try that. Okay, let's try that. It's running, running, running. Okay, the fourth one is found. Still running. It seems it takes kind of more than 20 seconds. Okay, how long does it take? Maybe 20 seconds to go up to 20,000, and we got 4 numbers. You can check yourself that this is correct. Okay, so anyway, we find a way to find prime numbers. And we have a feeling that it is not so fast. So in next lesson, we will try a faster version, and let us compare the two methods mathematically. Be sure to come back. That's all for today. See you next time. Bye bye.